Hello, I'm Danny Moss with Mahr Incorporated. Today I'm presenting the webinar titled Introduction to Surface Finish Filtering, Selecting the Correct Wavelength Cutoff. During the presentation, please feel free to input questions you may have into the question box in your GoToMeeting control panel. All questions will be answered following the conclusion of the webinar. Let's start our discussion of selecting the correct roughness wavelength cutoff, or just cutoff for short, by looking at these two traces. Both traces appear similar and both results are reasonably close in value to one another. But what is different between the two traces is the cutoff. The cutoff is one of the most important selections for correct surface finish evaluation. With an incorrectly selected cutoff, the surface evaluation could produce results that make a good part show bad or make a bad part show good. During this webinar, the proper selection of the cutoff will be discussed. By the end of the presentation, you should be able to correctly assess your profile and select the correct cutoff. Here's another example showing how evaluation of a roughness profile is affected by the cutoff selection. In the first evaluation at the top, the trace is filtered with a cutoff of 0.8 millimeters. Then the parameters RA and RZ are evaluated. In the second evaluation, the same trace is filtered with a cutoff of 0.25 millimeters. Notice the difference between the RA and RZ of the previous evaluation. In the third and final evaluation, the same trace is filtered with a cutoff of 0.08 millimeters. And the parameter results are now close to 1/2 their original values from the first evaluation. So by changing only the cutoff, the parameter results were reduced to close to 1/2 their original values. So, what is surface finish filtering? Surface finish filtering is the method by which a surface profile is separated into short wavelength and long wavelength components. Let's take a look at the total profile to the right. This profile represents an as-traced profile. When this profile is filtered, two separate profiles are generated. The waviness profile, composed of only the long wavelength components of the total profile, and the roughness profile, composed of only the short wavelength components of the total profile. In this example, it is easy to see that the waviness profile has been removed from the roughness profile, or I could just as well say that the roughness profile has been removed from the waviness profile. In either case, both the waviness and roughness profiles can now be used to evaluate surface finish parameters. Now that we have discussed surface finish filtering, we are now ready to discuss the operating principle of the cutoff. As we have already discussed, the choice of the cutoff is important to correctly separate roughness and waviness components. Let's look at the profile on the right. This profile has two distinct wave components, a long wave component and a short wave component. When the selected cutoff is too long, waviness components may enter into the roughness profile. This could lead to a good part being labeled bad. If the cutoff is correctly selected, then the waviness components are removed from the roughness profile. On the other hand, if the cutoff is selected too short, then the roughness profile will be over-filtered and important roughness data may be removed. To the right is a roughness profile that was filtered using a 0.8 millimeter cutoff. But if this same profile were filtered using a 0.25 millimeter cutoff, then notice that the profile height has been significantly reduced. Any height-based roughness parameter would artificially be lower in value when evaluated from the lower profile. In this case, a part that would normally fail could actually pass. Now we will include a discussion on the effects of the cutoff. Different measuring systems can be set up to measure a profile in a variety of different methods. Different methods include using a full pre and post travel, a half pre and post travel, and even no pre and post travel. The trace length and the pre and post travel are typically automatically set as a function of the cutoff. For example, the trace on the right is a standard 5.6 millimeter trace. This trace is broken down into 7 sample lengths. When the profile is filtered, the first and last sample lengths, the pre and post travel, are removed. What is left is the 4 millimeter roughness profile. This is an example of a full pre and post travel trace length. What is important here is 1, that the roughness profile can be shorter than the original trace, and 2, the waviness is removed from the original profile. There are 2 standards that present guidelines for measuring, filtering, and evaluating surface finish profiles. The American Society of Mechanical Engineers B46.1 and the International Organization for Standardization 4288. The selection of the cutoff, or specifically the roughness wavelength cutoff, is the topic of discussion for this presentation. The ASME B46.1 states that the cutoff should be indicated on all drawings requiring surface finish evaluation per ISO 1302. If the cutoff is not specified on the drawing, both standards follow a method for determining the correct cutoff. There are 2 methods used in the standards for determining the correct cutoff if the cutoff is not indicated on the print. The choice of the method used is determined by the type of profile that is being evaluated. Both standards break down all profiles into 2 types, periodic and non-periodic. This is an example of a periodic profile. A periodic profile is a profile that has a recurring feature, such as that of a turned surface. The profile above is a 2-dimensional example of a turned surface. A 3-dimensional example is shown to the right. Notice that on the 3-dimensional surface, there is a predominant direction of lay. The preferred direction of tracing is direction 1. If a trace were made in direction 2, then the repeating feature would not be seen in the roughness profile. This is an example of a non-periodic profile. A non-periodic profile is a profile that has no discernible recurring feature, such as on a ground or polished surface. The profile above is a 2-dimensional example of a polished surface. A 3-dimensional example is shown to the right. Notice that on the 3-dimensional surface, there is no predominant direction of lay. Therefore, there is no preferred direction of tracing. If a trace were made in direction 1 or direction 2, similar profiles would be acquired. If the profile is periodic, then the following method is followed by both standards. First, estimate the RSM value from an unfiltered profile. In both standards, there are tables that show the selection of cutoff related to the RSM parameter for a periodic profile. A summary table for both periodic and non-periodic cutoff values is shown to the right. Now locate the column for the RSM parameters and search for the range of RSM values where the estimate falls. Now find the corresponding cutoff that should be used for the estimated RSM. Let's walk through an example of selecting the correct cutoff for a periodic profile. First, estimate the RSM parameter. In this example, the estimated RSM is 0.4 millimeters. Take this estimated RSM value and search the table for the range of RSM values where the estimate falls. The cutoff for this range of RSM values is 0.8 millimeters. Now, measure the profile and filter with the 0.8 millimeter cutoff. Select the RSM parameter to be calculated. Last, verify that the new RSM value fits the same range as the 0.8 millimeter cutoff. If it does, then the 0.8 millimeter cutoff is the correct cutoff to use. If the new RSM fits in a different range, repeat the above procedure with the new cutoff until the RSM value and the selected cutoff are in agreement with the table. If the profile is non-periodic, then the following method is followed by both standards. First, estimate the RA value of the unknown profile. For example, using the total profile trace we discussed earlier. In both standards, there are tables that show the selection of the cutoff related to the RA parameter for a non-periodic profile. Now, locate the column for the RA parameter and search for the range of RA values where the estimate falls. Then, find the corresponding cutoff that should be used for the estimated RA. The ISO 4288 standard also has non-periodic cutoff tables for use with the following parameters: RZ, RZ1 max, and RSM. The above procedure is the same when using these parameters. Let's walk through an example of selecting the correct cutoff for a non-periodic profile. First, estimate the RA parameter. In this example, the estimated RA is 1.5 microns. Take this estimated RA value and search the table for the range of RA values where the estimate falls. The cutoff for this range of RA values is 0.8 millimeters. Now, measure the profile and filter with the 0.8 millimeter cutoff. Select the RA parameter to be calculated. Last, verify that the new RA value fits the same range as the 0.8 millimeter cutoff. If it does, then the 0.8 millimeter cutoff is the correct cutoff. If the new RA fits in a different range, repeat the above procedure with the new cutoff until the RA value and the selected cutoff are in agreement with the table. The final step, per both standards, is to measure and evaluate the profile with the next shortest cutoff if it has not already been tested. In the example before, the cutoff was determined to be 0.8 millimeters. So the next step is to measure the profile and filter with the 0.25 millimeter cutoff. If the 0.25 millimeter cutoff and RA value are in agreement with the tables in the standards, then the 0.25 millimeter cutoff is the correct cutoff to use. If the 0.25 millimeter cutoff and RA values are not in agreement with the tables, then the previously determined cutoff of 0.8 millimeters is the correct cutoff to use. A graphic summary is provided to help visualize this process. For a periodic profile, estimate the RSM parameter. Locate the correct cutoff from the standards table that correlates to the estimated RSM value. Measure a profile and filter using the cutoff from the table to determine a measured RSM value. Verify that the new RSM value correlates with the selected cutoff in the table. If the two correlate, then this is the cutoff to use. If they do not correlate, then use the new RSM result and determine a new cutoff from the table. This process will be repeated until an agreement between the RSM and the cutoff in the table are reached. You can now see the process for the non-periodic profile is almost identical to the periodic profile. The first difference is the use of the parameters RA, RZ, RZ1 max, or RSM, depending on which standard you are referencing. The second difference is the final step of measuring the profile with the next shortest cutoff. Now, let's re-examine the first slide we looked at in the presentation. Which of these two measurements conforms to the standards? To answer this, we must look at the tables in the standards for non-periodic profiles. By comparing the cutoff and the RZ value from the upper trace, it is easily seen that the cutoff and the result value agree with the table. By comparing the cutoff and the RZ value from the lower trace, it is also easily seen that the cutoff and result value do not agree with the table. Therefore, the correct cutoff selection is 0.8 and the upper trace is correct. Here is another example of selecting the correct cutoff. These two results represent two profiles evaluated with two different cutoff values. The upper set of results was evaluated with a 2.5 millimeter cutoff. The lower set of results was evaluated with a 0.8 millimeter cutoff. Again, which result is correct? To answer this question, we must again refer to the appropriate tables from the standards. When we compare the values from the upper result set to the table, we find that with the 2.5 millimeter cutoff, the parameters are in agreement with the table. When we compare the values from the lower result set to the table, we also find that with the 0.8 millimeter cutoff, the parameters are in agreement with the table. So both result sets are in agreement with the tables. But recall the last step for determining the cutoff for a non-periodic profile. The profile must be measured and evaluated with the next lowest cutoff. If the next lowest cutoff is in agreement with the results, then this is the cutoff that should be used. Therefore, the lower result set is the correct result set. In this final example, a 0.8 millimeter cutoff was assumed since no cutoff was indicated on the print. Prior to the ASME B46.1 1995 edition, the default cutoff of 0.8 millimeters or 30,000ths of an inch was assumed if the cutoff was not indicated. Now that you have seen this webinar, you know that this assumption should not be used. In this example, the 0.8 millimeter cutoff filtered the 5 millimeter periodic component from the roughness profile. What was evaluated was a roughness profile that had an RA of 1 micron. If the methods and the standards presented in this webinar had been followed, this profile would have been determined to be a periodic profile and the evaluated RA would actually be around 6 microns. Here are some final notes. We have covered how to select the correct roughness cutoff, and now it is important to make sure that your system is using the correct cutoff. On many systems, changing the trace length will also change the cutoff. This is because many systems will adjust the cutoff length to maintain 5 sample lengths in the roughness profile. This is particularly true when the trace length must be made shorter due to the available surface to be measured. So care must be taken to ensure the correct cutoff is used for evaluation of the roughness profile. When no cutoff is specified, each part could potentially be evaluated with a different cutoff. Remember, the standards indicate that either the RA or RZ or RS sub M must be compared to the appropriate tables to determine the correct cutoff. Also, long wavelength components are important too. Other measuring methods need to be employed to ensure that these longer wavelengths are evaluated as well as the short roughness wavelengths. Sometimes a designer will specify a longer cutoff on a surface for more conservative control. Remember, a longer cutoff will include longer wavelengths in the roughness profile. If the RA, RZ, or RSM values were compared to the tables in the standards, the use of a shorter cutoff may be determined. But since the designer implemented a specific cutoff on the print, this cutoff should always be used. In closing, thank you for taking time to join me today. I hope that this webinar was informative and enjoyable. Please input your final questions into the question box, and they will be answered at the conclusion of this webinar. Thank you.